Right, so for those of you who don't know me, I'm Malcolm McCulloch. I'm based at the University of Oxford, and today's session is going to be looking at how do we use the Internet of Things technology to enable and to help develop a low carbon energy economy. If we go to the next slide, please, Elizabeth. Okay, so we've done the welcome, and I just wanted to say that what we'll be looking at today is IoT, and we've got a wonderful agenda. I'll be giving a quick overview of why I think IoT is going to be really important in the emerging energy economy. It's just one view. I'm sure many of you have other views, and just shows you the richness of the space. Andy will give us a quick overview of the portfolio of what's actually been funded through the pitching. And then we got some showcases, some wonderful showcases from, first of all, Dave Howey is going to be looking at batteries and big data. Then Dan Rogers is going to be looking at NETRIM restrictions on an IoT-based microgrids and to see how IoT can be used in microgrids. Then Prof Dan Gladwin will be looking at data-driven battery degradation. And Avinash Vijay will be looking at baselining for smart energy systems. Each of those will be able to have one or two questions, and then with time permitting, we'll then move on to our panel discussions. And we've got Mel Bryce from SSE, Priya Bhagavati from University of Oxford, and John Clark from University of Sheffield. And that panel discussion will be, first of all, giving a few insights from each of those people, and then kind of opening up questions to the audience and to have a debate to see, to explore some of the challenges around IoT and energy space. And we aim to finish by about 3:30 with some closing remarks. Thanks, Elizabeth. Next slide, please. So let's start off with looking at what is the role of IoT in energy systems. So the first question is, next slide, please, is what is IoT? And this is a really good question. And there are probably as many variations on the theme as there are people that you talk to in the space. But basically, we've tried to take a broad overview and to say it consists of at least 4 different aspects. First of all is data gathering. And this is looking at network sensing devices that gather and share information over a large area. Secondly, it's about data transmission, normally wireless, but it could be wired from the sensor, and it could be going to a cloud where there is data analysis. And the data analysis often starts with data cleaning to make sure that we've got a high integrity of the data, and then analyze to get some insights on how we can use it. And then the last point is to say, once we've got those insights, can we use IoT to actually execute decision and control? And hopefully throughout today, we'll see what the uses of IoT is. Can we have next slide, please? So if you look at the consideration of the energy system, this is kind of like for most of us what a power system looks like, and that's a big, ugly power station. This happens to be in Didcot, which is near us. And one of the key things you'll notice is that towards the back, you've got the main turbine hall where the energy is generated. But if you look in the front left-hand, in the foreground, on the left-hand side, you see a big lump of coal, and that is where you basically that acts as a large energy store for the system so that we can generate on demand. Next slide, please. And so a very schematic way of looking at what our traditional power system looks like is we've got a generator, which is generated in certain locations, traditionally often near coal fields. And then we have a transmission and distribution system, which the transmission system takes it over long distances, and then the distribution system spreads that energy over large areas to consumers, which is on the right-hand side. And then what we do is we gather, we have retailers that gather up the money from the end users and distribute that both back to the generators and to the distribution system. That's a kind of like a really high-level, simple way of looking at things. Next slide, please. And in particular in the UK, this is what it happens to look like. We can see our transmission grid in England on the left-hand side, about 400 and 275 kV network. We then, on the right-hand side, you can see the distribution networks and how they're divided into the different areas and how we actually spread that out. And then the energy retailers typically used to be the big six. Now probably those names have probably changed a little bit since I prepared the slide. Next slide, please. The challenge that we have is that we based on the energy system used to be based on coal and latterly gas, and that used to produce CO2. And as we can see from this picture, our atmosphere is actually not as thick as we think it is. And so therefore, we're actually making a significant impact on CO2, which is leading to our climate change challenges. Next slide, please. So we're going to have to move from coal to something like wind and solar and possibly nuclear. And the idea, but the challenge with this is, if we go to the next slide, please, is that we can start off thinking about just dropping in the switching out the coal and gas and dropping in the nuclear, solar and wind. And that seems like that's all we need to do. Next slide, please. However, this is not as straightforward as we want to, because not only are we doing that, but as we're decarbonizing the system, we're also increasing the load on the system with, you know, ground and heat air source, ground source and heat source, air source heat pumps, electric vehicles, and increasing amount of electronic load. Next slide, please, both competing and otherwise. And so what we need to find is that actually we now need to balance the system, because unfortunately the generation doesn't actually generate when we want it to, and this, you know, in the middle of the night you can't use sunshine to actually power the system, and also when it's not windy you also got a challenge of powering the system. So the challenge now actually goes up a notch from just moving energy through space. Now we've got to think of moving it through space and through time. And that we enable through what's glibly called balancing services, which basically enables us to either shift energy usage patterns or to be able to store energy and then reuse it at a later stage. Next slide, please. And what we find is that quite a lot of the key components that may well be used in the balancing service and end use are multi-services. So for instance, it might be air source heat pumps, which we can actually adjust their usage patterns to actually match both the generation and yet provide the energy requirement to keep the building either warm or cold. Or it could be things like smart charging for electric vehicles, or if you want to be even more adventurous, if you're looking at vehicle to grid. The main thing is that there are lots and lots and lots of these appliances that potentially can come through. Just to give you an indication of how important they are, is that if you look at something like the potential power capacity of the EV fleet by 2024, which happens to be when the end of this parliament is, it's the power capacity of the EV fleet in the UK will be larger than that of the nuclear fleet. By the time we get to the early 2030s, there'll be sufficient energy storage in electric vehicles to produce the total electricity consumption today for 2 days in today's terms. Obviously, it'll be less because the energy requirements are going up through time. So these lots of small assets, although they're small and they don't look very big in terms of they're not rated in megawatts, they're more rated in kilowatts and kilowatt hours, because there are millions of them, they are going to be important players in the future system. So the question is, we need to be able to enable them to participate well within the system. Next slide, please. So what that means is now that we now need to be using information to be able to understand when is the energy actually being generated? Are there any constraints on the networks, both transmission and the local networks? When do we actually need charging? When are the charges going to take place? When do we actually need to use the different appliances? And so the scale of the challenge that we have here, just in terms of the amount of data that we're going to have to be using in the power system just to keep it going in the most efficient way, is going to require a substantial amount of data, and hence IoT, I believe, is going to be one of the key enablers of this space. Also, the slight challenge that we have is that there's no single actor to whom the data goes to. There are potentially multiple actors that actually could be using the data, both in terms of aggregators, but also in terms of retailers, suppliers, and people who actually manage the equipment and manage the batteries and the like. So this is going to be a really interesting and challenging space. Next slide, please. So some of the top 5 challenges I think that we may well be coming through is that there's going to be lots and lots, and I'm meaning terabytes of streaming data that we're going to have to look and start managing. It's also going to be more than just simply energy data. It's also going to be about performance data and state of health data and other things that is going to be moving around in the energy system. One of the key issues to ensure, how do we ensure both security of the message being sent, but also privacy, so that individuals can only release the amount of information that they need to release and remove the concerns over privacy. The fourth issues are going to be both open and interoperable, which is going to be enable lots of new players to come into space. And you can see there's a slight challenge with how do we resolve both 3 and 4 together, because they're kind of slightly contradictory. And the last aspect is to say is there's going to be not just a single creator of value. There's going to be multiple places where we're going to have to, this information is eventually going to have to land. And so this starts to become quite an interesting challenge in this space. So hopefully that gives you a quick overview of why I think that IoT is going to be really critical for the energy system going forward, and also some of the challenges that we have going through. Next slide, please. So if you, that's the end of my little brief introduction, and we're now going to move over to Andy, who's going to give us an overview of that. If you have any questions, please drop them into the chat function. I'll be looking at them. Stephen has made a very good suggestion, Stephen Potter, to say, just introduce yourself in the chat function as well if you want to. If you put a question, just start with a Q so that I know that that I'm looking at a question, not just as an introduction. So thanks a lot, and over to Andy.
Thank you very much, Malcolm. So that sort of gives you an idea of the complexity of the problems and the opportunities of introducing IoT into an energy system. The universities have similar issues. Over the last few decades, perhaps even more, innovation by universities has often been driven by increased specialization and depth of understanding. And it's worked well because the UK is still a global leader in innovation. In addition, university structures are built around longer term projects and learning. So for instance, a sort of PhD approach of 3 or 4 years. However, this approach to innovation is not fit for purpose when it comes to digital innovation, where speed and multidisciplinary approaches are required. Can I have the next slide, please? So this is where Pitch-In is starting to sort of do something. It's funded by Research England's Connecting Capability Fund, and it aims to provide learning on barriers and how to overcome them to knowledge exchange. It's also, given its name, about connecting capabilities, both within universities, across universities, and across stakeholders in the innovation community, whether it be that companies, public bodies, anyone. It's a collaboration led by Sheffield and with the universities of Cambridge, Newcastle, and Oxford. And its core is some mini projects to test how barriers can be overcome. It would have been nice to have been very strategic and sit down and have a good think about what the barriers were, and then to design some projects to see how we could overcome the barriers. But given the timescales and budgets of Pitch-In, that approach was not possible. So instead, we sought projects that will provide learning on barriers and where sustainable connections could be made. And we were essentially seeking interested professors with interesting projects. And I think this approach has worked very well because the interest of the projects has kept Pitch-In going despite COVID, but also there's an incentive on the professors because they can see direct application to their future work. The mini projects have included partners from academia, industry, public sector, and professional bodies across the board, and each one mini project is pretty unique. Pitch-In runs from April 18 to June 21, with the final reporting to September. The astute amongst you will realise it's still ongoing. So the final analysis of the barriers and how to overcome them is ongoing. But today is about the sort of building bricks of the project, which is about the mini projects. Next slide, please. So Pitch-In is a program that isn't just about energy. It's got 4 different strands: health and wellbeing, energy systems, smart cities and manufacturing. And we're holding an event on each one of those. The health and wellbeing was last week, energy systems today, smart cities next week, and manufacturing the week after that, if you're interested. But the common thing about each of those 4 sectors, apart from the fact that universities have good strength in all those sectors, is that they are seeking to apply IoT into legacy systems. All these systems are ongoing. And the question is, how on earth do we introduce IoT into a market that is already there but needs to change? And the idea is that by doing a project in health and wellbeing against a certain barrier, we might learn something that's relevant to some of the other legacy systems. And that's the work that needs to be done over the next 6 months within the Pitch-In management team. Could I have the next slide, please? So the first question is, which barriers are we trying to target? And we had some various studies done at the beginning of Pitch-In. We consulted a lot of stakeholders, and he came up with a list of 9 groups of barriers, so a horrendous number of them, which I have unilaterally collapsed to 7 of them in here. But it's just a key to get a little bit of a feeling of what they are. The first is around resource and data access. This is anything to do with data. Most people working in a sector or applying an IoT in a particular sector are not data specialists, they're the sector specialists. And so access to data, how to share and use, the issues of privacy and indeed security are all very big barriers. The second group of barriers is dispositional. The universities tend to have inflexible systems, as I've mentioned, longer term projects they're used to. The commercialization processes have built up over time and have inertia built into them. And crucially, I think universities are not a place to go if you want to be a software engineer that wants to make some money. And so there is a critical shortage of skills within the university itself in terms of professional software capability. Educational, again, because IoT is not a discipline, and indeed data skills aren't a discipline. They're scattered over several departments, maybe statistics, computer science, engineering, maths. And so there's no single home for the knowledge base around IoT. And that creates problems for people trying to apply it. The next group is around connectivity. IoT does involve disparate functions and parts of an organization. As I've said, there's no single focus. But within a university, this requires you working across departments, which effectively are cost centers. In industry, it requires you working across profit centers. So you're working directly against the crucial drivers of where an industrial company is working. So to try and find and work with relevant colleagues is a really difficult issue. Infrastructural issues are also very important, including security, the lack of common platforms, and the need for interoperability. The classic of that is the first generation of smart meters, which are totally inoperable via a second supplier. So it is a key issue. The next one is around business cases, the deployment of systems, IT systems into a legacy system. There have been numerous programs which have introduced very expensive IT systems with all sorts of promise that have crashed and burned. So the question is, how do you make a business case that is really believable? And what can you do to make it IoT, the introduction of IoT, cheap? And then, of course, there are technical developments which are needed. Certainly the categories are not simply pigeonholed or distinct. There are many overlaps. So one of the team's activities that we'll have to do over the next 6 months is to have a hard look at this list and see if we can rationalize it or draw out some key lessons. Could I have the next slide, please? So what's the energy portfolio specifically done? We've looked at various barriers. We've had various studies done. And we had an initial meeting of stakeholders to identify potential mini projects and barriers. The really interesting thing, and I'll come on to it in a minute, is that that initial meeting very quickly diverted into the needs of data, how to analyze, how to clean, etc. And so it was quite apparent that the really important one was, and the barrier was around data. The energy portfolio has funded 9 mini projects, and they're led by Oxford, Sheffield and Newcastle across the piece. I think part of the fact that the approach we took in terms of seeking out interested professors has really helped during the COVID crisis, because I'm pleased to say all 9 mini projects have come to an end, and successful end, maybe not in quite the way they intended at the start, but there's been a lot of pivoting and some really good results have come out of them. 3 of those mini projects you hear about today. I'll talk about the others in a second. There is 2 ecosystem projects which are rather bigger. The one from Oxford you will hear about later today, and the one from Sheffield is really about developing the Sheffield campus as a energy management site, and to gain access to data both for teaching and for energy management. We've also funded some internships of students, both doctoral students and undergraduates. And these have been with companies, like a local company just around the corner from me, Atomate. They've also been with pitch-in projects, attached to pitch-in projects. And they've also worked with professors who have an interest in IoT who haven't got a pitch-in project. And I'm pleased to say they were all successful. I think the internships did good work for either the company or the professor involved, but also, much more crucially, I think without exception, they've all said they want to go on and place their career in something to do with IoT. So a very successful that. The dissemination activities have been various of them, including a lot of academic papers coming out, and the website is the long-term repository for the lessons. That's the place to go and see when I'm going to mention a few projects now. Next slide, please. So this is my completely subjective and totally unscientific approach to what I think has come out of the barriers and where we are. So there might be people who disagree with me. But I think data resource undoubtedly is the top barrier. It was identified in the initial meeting. 2 of the projects today you'll hear about is in this area. There's a 3rd one around data readiness within IoT for energy, which looks at metadata requirements for IoT devices and data standards with a view to promoting interoperability. On that, you can look at the website. That is probably, to me, the key barrier that we've attempted to try and resolve. The dispositional barriers, we haven't done very much, but linked to pitch-in, and as a result of pitch-in, Oxford University has set up a group of software engineers whose dedicated role is to support professors in both developing programs and how to use their data. So there has been a spin-off benefit there from pitch-in. Educational, undoubtedly, everyone's learned a lot across the project, both the mini project teams and also the interns. Connectivity, I think, is another key one that's been addressed by by pitch-in, and all projects have been tackling to some elements this barrier, and has evolved good connections, and it's very encouraging to see a lot of them look like long-term connections that can go on to the future and support work. The infrastructural issues we haven't really tackled. That was more or less in the background, and there's not much to say about that. But the business case one is a key one. And another example project has been in terms of building energy management. You can manage a building's energy from the cloud. You can control it, but the key thing is, how do you model a building before you get there, and how do you get enough data cheaply to build a model to start with? And that's one of the projects that will be on the website. Another one is a high fidelity energy monitoring project at Sheffield, which again is worth looking at on the website when it comes out. And finally, yes, technical, there've been technical developments here throughout as well. 2 projects at Newcastle, both looking at sort of energy harvesting, one with Northumbrian Water, looking at how to remotely monitor water meters, and one with Royston, a small company, who makes sensors that you attach to marine diesel engines for monitoring. Both those involved technical developments. And the project from Dan Rogers, I think you could also argue, is in this group, which you're going to hear about today. Next slide, please. So, as I said, we've still got work to do in terms of bringing all the projects together and getting some insight into the final barriers. That's what I've just said is my own personal opinion. But there will be a conference on the 16th of June where some further thinking around the barriers will be done. And I think with that, I'll stop.
Thank you, Andy. Andy, you've been lucky. I haven't seen any questions coming up, so I'm just going to ask you one quick one, which is, what do you think has been the greatest success for pitching from your perspective?
I think it's the realization of the multidisciplinary teams to tackle the data problem. I think there's several teams have been formed, and there's been some really outstanding successes. And it's finding a way of working across current structures. That's the key. That's the key success, I think.
Thanks, Andy. Great. So we're now going to move on to our next part of the agenda, which is looking at the mini project showcases. And first of all, we're going to start with Professor Dave Howey, who's from the University of Oxford, and he's looking at batteries and big data. We'll then move on to Dan Rogers, looking at NETRIM restrictions in IoT-based mini-grids. Dan Gladwin, looking at data-driven battery degradation studies, and Avinash Vijay, looking at baselining for smart local energy systems. Once again, can I please request that if you have any questions, and I'll encourage you to ask some questions, just stick them in the chat and I will keep track of them. So over to you, Dave.
Thanks, Malcolm. Let me just get my screen share on the go. All right, everyone see that okay? Yeah, brilliant. Okay. Well, it's great to be here, and it's great to see so many people tuning in. I'm aware I've only got a few minutes, so I'll crack on. But my name's David Howey. I'm one of Malcolm's colleagues, an associate professor here in engineering in Oxford. And I have to say, first of all, a huge thank you to the pitching team and Andy Gilchrist for making this happen. It was, 3 years ago, it was a relatively kind of small project, which isn't to say it was unimportant, but it's really developed, in my case, in something fantastic. And so I just want to really thank Andy in particular. All right, so I'm going to be talking about batteries and big data. That's a pretty broad topic. I'll in particular be focusing on how we handle lab test data in our battery lab here in Oxford. And just to kind of give you some context, these pictures show some battery test systems in the lab. The one at the bottom is actually one of my PhD students, and she's generated tens of gigabytes of data during her PhD. So that's not big data from a kind of CERN physicist point of view, but it's still pretty big data from the point of view of just handling stuff in a sensible way and not using Excel spreadsheets. So that's kind of where we're at. Okay, so I think just to explain what the challenge is that we were trying to address in this project, the challenge is that lab battery testing generates data from lots of different pieces of equipment. And so, for example, in our lab, we have about 5 different manufacturers. All of these systems have their own proprietary software. They have their own proprietary data formats. And therefore, a typical workflow to actually analyze data from battery testing is completely nuts. It's totally crazy. So, for example, you would go onto the system of choice, find the files you need, export the data to CSV, transfer them to another computer, search for what you want in that data, then write some analysis code in MATLAB or Python, generate a plot, then go back and find some other data that you want to compare to the first data set, repeat the whole thing again, do that for every single hardware type. It's a complete waste of time, and we have to do better. And so we realized this a few years ago, and this project came along, and it seemed a perfect fit. And just to kind of give a kind of broader view on that, this problem is recognized by many people around the world working on batteries. And if we compare ourselves to, say, what's happening in the pharmaceutical industry, I think it's fair to say that the battery community is very far behind. And this results in kind of incremental gains and lost productivity. So, for example, it's taken 30 years from initial commercialization of lithium-ion batteries to actually achieve the energy and power density that we have today, which is amazing. Lots of people have done lots of great work there. But it took the Human Genome Project about a decade to go from nascent idea to public release of the first genome data set. So I think the battery community could do a lot better on data. Okay, so the project that we were involved with here was a project that aimed to basically try and develop uniform data practices and tools that work across all of our different pieces of equipment in the lab in order to improve things so that we can analyze data much more quickly and share it and collaborate, etc. So the tool that we have been developing is called Galvanalyzer, which is a bit of a mouthful. I've realized that different people around the world really struggle to say that, so we might have to change the name at some point. But anyway, Galvanalyzer it is. And what this tool does, you can see on the picture here, we have these things called harvesters, which are basically small pieces of code that's sort of bespoke written for each different piece of equipment. And they sit and suck data from each separate bespoke manufacturer and then translate that into a unified kind of format, put it on a Postgres database, and then we have a web app that people can use to look at that data. And there's an API, so you can easily get access to the data from Python or MATLAB or whatever. And crucially, that data is then completely unified. So it doesn't matter whether you're using, equipment manufacturer A or B or C, it doesn't matter. All the data, you can search it in a completely unified way. And so this, I don't expect you to be able to read this, but as part of this process, we've had to develop quite a flexible schema for the data, which contains the key information that enables sharing. So for example, here there's experiment.column type, and we actually have different types of columns so that it's very flexible, and you've got standard and non-standard things. So there's voltage and current in there, but you could also put in frequency domain data, for example. On top of that, we've had to think a lot about metadata, because one of the things that these pieces of equipment don't do is they don't actually do metadata at all. So for example, the equipment that you plug your battery into to test the battery, it doesn't say, oh, which battery is that? Does it have a unique ID? Who's doing the experiment? And what's the purpose of the experiment, etc. So we've had to think really hard about what the minimum set of metadata is that is useful, but not go completely overboard so that we have a straitjacket which no one can use. And these are some of the examples of the key pieces of metadata that our system kind of forces the users to input. Okay, and some of the results. So these are just some screenshots from the tool that we've been developing. So as I mentioned, the tool Galvanalyzer has this front-end harvester for each different type of equipment. And so you can see here a list of different data sets from different types of equipment. And if you kind of click on one of those data sets, you can then go in and have a look at it. And so here we see, for example, some battery voltage, capacity, current data for a particular data set. And you can see kind of the metadata and timestamps and all that kind of thing as well. And the tool that we're using to do this is called Redash. You might have come across it. If you haven't, it's a brilliant tool for actually connecting to a database or other generic data source and quickly writing queries and visualizations without having to get into the nuts and bolts of things like account creation and user management. So Redash has been really excellent for us. And you can zoom in, you can play around with different web apps for visualizing the data in different ways. So in terms of the lessons that we've learned through this project, so I think the first thing is that we've had to adapt as we've gone along. When we originally started the project, we thought that it was going to be mainly a kind of GUI with a database behind it, and then through the GUI you would generate various plots and things, and they would be kind of publication ready, so you wouldn't have to do any more post-processing. And what we've realized is that that's not really what we want. What we want is a unified database with a simple GUI that lets you check, have I got the right data? But then an API that you can use to pull the data into your software of choice, whether it's Python or MATLAB or whatever. So we've kind of adapted as we've gone along, and this just shows some of the Python API script that we've written in that process. Second lesson, I think, is that we've pulled in the professionals to do it right. And this is also just a nod to these two people. So on the lower left is Luke Pitt and then Martin Robinson. So Martin is currently working on the project. These are both software engineers. And I think we quite quickly realized at the beginning of the project that we didn't have the capabilities in my team doing battery research to do a good job on this. And as Andy alluded to earlier, Oxford have set up a software engineering group, and they have been absolutely brilliant for doing this properly. So that means GitHub version control, proper issues, proper documentation, installation, and all that kind of thing. Third thing in terms of lessons is that we've built some wider links, and actually I'm really excited about this project because it's gone way beyond the UK. So we've been building links with Sandia National Labs in the US, who put together this website that you can see here called Battery Archive, which actually has some similar things going on behind the scenes, although it was originally a slightly different purpose. And so we've actually pulled some of their code across, and we're using some of their stuff related to the Redash tool that I mentioned. And we're talking about in the future, maybe bringing the two projects together. So building those wider links has been crucial for kind of generating momentum, keeping things going. So in terms of next steps and kind of overall thoughts and recommendations, I'd say, data management, it doesn't sound like a glamorous topic, but it's really important. And actually, in this case, it's led to much bigger things than I would have expected 3 years ago. So for example, at the moment, we're actually working on a perspective paper. This is a kind of screenshot, which is called Principles of a Battery Data Genome, which addresses a lot of these issues and wider issues around the need to accelerate progress in learning and battery innovation through data. And this is a combined effort with lots of US national labs and universities in the US, Germany, and other places. So really exciting. This paper is still under review, but I think when it comes out, it'll be quite high profile. Second thing is we will be open sourcing our code at some point soon. We're just making sure that the testing is going well, and that the documentation and all that kind of stuff is in place before we do that. But really excited to kind of build more of a community through open sourcing as well. And then finally, of course, we want to use this as a tool to do better battery research, to analyze and understand our data and get results more quickly. These graphs just show some results from one of my student projects, actually the PhD student on the front slide, that were published last year, just to give you a flavor of some battery data. And that's it. So I just want to say, thanks for listening, and thanks for the funding for Research England, Andy Gilchrist, who I mentioned, and particularly Martin and Luke, the software engineers who developed this, and Adam in my team. And just as a side point, well, there's some web links here if you're interested. So that's my group website, an archive preprint about this project. But also we are doing lots of big data work on real live data outside the lab from batteries in the field. We're currently working with a company called Bbox on sub-Saharan African batteries, and actually processing something like 500 million rows of data to try and understand battery health in the real world. So if you're interested in that, drop me a line, and we should have some work coming out on that soon. Thanks very much.
Great. Thanks, Dave. That's great. No specific questions from the audience, but the one I wanted to ask you was, were there any unexpected insights from this project that you got?
Well, that's a good question. I suppose, and I'm kind of preaching mainly to the academics here, but don't underestimate the importance of doing a project that may not on face value seem that glamorous. It probably lead to things which you don't expect. And if it's the kind of problem that lots of people around the world are also facing, then it's a great way to build a community and actually get sort of international links as well.
Thanks very much, Dave. So congratulations on that. Let's give you a quick round of applause. Thanks. I think some of you can clap. Next person is Dan Rogers, talking about IoT in microgrids. Dan, over to you.
Hello, everyone. Thanks for the introduction, Malcolm. And I won't repeat everything that Dave said in terms of thanking the pitching team for their support, because that has been very valuable and is what has allowed us to do these projects. So thanks very much again, especially to Andy, who's based at Oxford. So I'm going to talk to you about network restrictions in Internet of Things based microgrids, which have the snappy title NETRIM. If I could have the next slide, please. So I suspect quite a few people will have an idea of what a microgrid is, although it's a somewhat nebulous concept, but the general idea is that we can build standalone electricity networks which embed generation loads and generation loads and energy storage, and there is likely, or there is almost always normally a requirement for some kind of control, overlaying control, command and control links. So these are often dedicated, can be dedicated wireless or wired links, but we were interested in seeing if we could do this over sort of a shared internet structure. The other thing to remember about electricity systems is that potentially the system dynamics are very, very fast, particularly for DC microgrids, where we can have problems with stability and voltage collapse over timescales of milliseconds. So we know in principle that Internet of Things type technologies can deal with slow data gathering and potentially do closed loop control at the kind of second timescales. But as we approach the kind of millisecond timescales, do these technologies stand up? I suppose that was one of the questions we were trying to answer here. Next slide, please. So we said we would build a sort of a test platform for doing research in this type of area. So we built a multi-node power electronics-based microgrid platform, which kind of sits on a bench. So this uses off-the-shelf field programmable gate array development board linked to some very low power electronics, only processing about 50 watts, which we can use as a kind of a representation of a larger system. And then we took this hardware, which was a fair developmental effort in and of itself, and we used it to demonstrate some example high-speed energy management algorithms. And the intention here is to explore the practical limits of the control speed that we could achieve on such hardware, rather than potentially simulating a system and trying to guess at what the variability is in there. So you know, the obvious one is that if we're sending packets over a shared Ethernet network, we can expect variable latency. And surprisingly, we get quite a lot of packet loss, even in relatively quiet networks, something we observed. And this can obviously have a big effect on system behavior, particularly if we are trying to do high-speed closed-loop control where we cannot wait for retries on data. Okay. So I should say, yeah, so on the right here, you can see a very simple sketch of the electrical network that we built in the network. It's a DC microgrid. It had some storage, some dispatchable generation, also known as a lab power supply, and various loads with some inbuilt energy storage in those loads. And the whole thing was linked together with gigabit Ethernet and a commodity Cisco router. Okay, next slide, please. So there's nowhere near enough time to go into the technical nitty-gritty, but basically the results we came up with were, I would say, a reasonable success. That might be a fair way to put it. So the 10-node system with the gigabit Ethernet backbone worked really quite nicely. So we could exchange data at the expected rates, and we got sub 100 microsecond point-to-point ping times, which is about the limits of what gigabit Ethernet can reasonably be expected to achieve. And on top of this, we built an energy management scheme, with a sample time of about 10 milliseconds. So our control loop time was 10 milliseconds, or we had 100 hertz update rate. And this allowed us, in this particular example, to share inbuilt storage in each load to support loads which experience sudden increases in their demand. So we concocted various scenarios where we thought this energy management algorithm might be useful, and we demonstrated that it did indeed work. I say we had partial success because even when we weren't stressing the network, we found that we did have to contend with quite variable latency and a fair amount of packet loss. I mean, we're talking sort of one in 1,000 packets when we set very short sort of windows for receiving a successful packet. We were losing quite a significant amount of data. And when we started, we didn't really worry about any of this stuff. We just said, well, let's just see what happens. And we found that actually it became quite difficult to run long-term experiments because the network would fall over, we would have stability problems. And I think that's something we're still thinking about, and we need to understand a bit more about, you know, why we're seeing that and how we cope with the types of packet loss that we started to see. So the diagram at the bottom is just illustrating our initial server client request and update mechanism that we were using. We were using UDP broadcast packets to synchronize our networks. Okay, next slide, please. Sort of as an offshoot project, which we started working on because it looked so promising, was this idea of, can we send data over the power line doing power line communication with a very minimal piece of hardware. And this was kind of the opposite end from the gigabit Ethernet type systems I've just talked about. This was sending data at only about 2 kilobits per second between converters on a large network. But the key thing here is this required truly no additional hardware because we used the inbuilt capability of the power electronics. That's the internal modulation unit, plus the current and voltage sensing at the outputs of these converters to exchange data. Actually, this worked really well, and we've got a nice compact piece of code that seems to work very nicely, and we're actually trying to protect this idea through Oxford University Innovations. On the right here, you can see a photograph of one of our early experimental setups. Next slide, please. So what lessons did we learn? I suppose in principle, gigabit Ethernet is a very, very capable technology, even though it's not necessarily designed for deterministic, communication. We easily manage point-to-point latencies of under 200 microseconds just using commodity hardware, even when the network was relatively highly stressed. Losing packets is just part of the deal with Ethernet, even wired Ethernet. That's interesting. And as of course, any control engineer will tell you, if you're pushing the bandwidth limitation of your system, you're always going to have, it's going to make it a more challenging control problem. And we certainly saw that as we went down into the millisecond regime of update rates. So things are fine if you just want to update stuff at 1 second, because you've got loads of time to do request and retry and all this type of stuff. But if you've got hard time limits on when you need your data back, things get a lot more interesting, I think. At the other end of the spectrum, we saw that actually in one particular network, we can do quite a lot of good work with a relatively low data rate of only 2 kilobits per second. So we kind of saw the extremes of extremes of communication here. I will say, I think we haven't done, it sounds, as well as Dave has in terms of doing knowledge exchange outside our research group, but I blame COVID for that, and I think we're trying to sort of fix that, especially as we start trying to commercialize some of or protect some of this technology we've developed. Next slide, please. So yeah, I think we've got kind of a bare bones system for testing these very fast energy management systems for microgrids. We might look at where the specific context where such a system might be particularly useful. The obvious one being data centers, because there's already a lot of communication infrastructure in there, but they also have rapidly changing loads and often constraints on loading in particular racks or something in the center as a whole. The other one I think is really interesting, and I've had a few tentative discussions about this, is for more electric aircraft. Future electric aircraft are going to have a lot of power converters on them. If we can use those power converters intelligently to reinforce the electrical network on an aircraft, then that might mean we can make all the converters a bit smaller, save some weight, save some emissions, carry more passengers, all that kind of thing. So, these are kind of nice to have additional technologies that could sort of incrementally improve performance of the sort of underpinning technological layer. If anyone else can think of applications for energy management in these very fast loop times, please do let me know. And of course, we're going to continue to pursue this new data link technology we've been developing. I think that's it. Next slide, please. Yeah, that's it. Thank you very much. It's a link to my group's website. Please feel free to have a look.
Thanks, Dan. That's great. One question, well, one pickup was from John Clark, and you may want to follow up with him afterwards, was also thinking about, he says these real-time issues crop up in also places like avionics, and to see what the crossover might be across that, and also to the automobile. But there they tend to have standardized on CAN bus or field bus. Any comments on that?
Yeah, I think absolutely. We probably did go in quite naive in terms of the underlying theory. We were trying to, we wanted to play around with the hardware, basically. Yeah, there is a lot of interesting work on yeah, modeling that kind of, you know, if you have a histogram of the likelihood of latencies, for example, you can use that to sort of put constraints on how likely your system is to fail and things like that. And I agree that if we do pursue this work in much more depth, I think we are going to have to review that field much more carefully. Definitely agree on that point.
Fantastic. Thanks, Dan. And if everybody wants to respond in the usual way, for Zoom, if you look at reactions, you can always put the clappy hands if you'd like to, and otherwise just do it. That'd be great. Thanks, Dan. Really appreciate that. And from one Dan to another Dan, and also from grids back to batteries, it's now Prof Dan Gladwin. Welcome, and over to you, Dan.
Thanks, Malcolm. Yeah, so again, a big thanks to the pitching team supporting this project. I'm going to talk about some of the battery degradation work we've been doing. Next slide, please. So the challenge I proposed in this mini project was we've done a lot of work on measuring degradation of batteries, particularly at grid scale, and we want to see if this can be done in real time with a large amount of assets, and how can the data from multiple assets enable better lifetime prognostics. One of the big barriers to this type of research for us is, where do we get all these big batteries from and this data from? So in this mini project, we joined up with partners to actually try and get this data. Picture there is a picture of a 20 megawatt battery system, Leicestershire. And on the right there is one of the cells that's in there, and there's over 90,000 of those cells. And this project is really about looking at the kind of the level you pull off data. So do you go right down to cell level up to the power system level to try and work out what's going on with the battery. And next slide, please. To put into context, just to ensure we understand this concept, is that the battery capacity estimation is important as the battery is used, and over time it will degrade, so its usable capacity will decrease. And on the right hand side there, showing a chart of some readily available Tesla data showing that each point is a particular vehicle and how many miles it's done on the x-axis, and the remaining range on the y-axis. You can see that you know, some vehicles done the same mileage have completely different capacities remaining in the battery. And this is what we're trying to measure. It's very important when we're using big grid batteries that we're using for supporting the grid, doing trading, that we understand the actual capacity of that battery at any given time. Next slide, please. So in this project, the key partner was Upside Energy. They've been around since 2014, so they've been around a while. We actually connect our grid storage battery through them. They're an aggregator onto the grid. They can connect up to 100,000 assets, which range from big battery systems for EV chargers, and even heating and cooling systems. Their platform allows you to match energy demand, provide grid services, and for trading. So it can actually be kind of a piece of middleware for traders, or you can actually tie up to National Grid to provide those services and balancing services. In terms of the academic partners, Dave Howey's already talked about the Galvanizer project, and what we want to do is take the data we're generating from these big batteries and put it into something exactly like he's described, and that's how it fits into this project. Next slide, please. So at the bottom there's a couple of pictures. Left-hand side is inside the University of Sheffield's big battery. In there's 21,000 cells. And what we do is we put this battery into operation, providing grid services, and we've been collecting this data since 2015, since it came on board. With this system, we can collect everything right down to the cell level. Quite recently, we've enabled ourselves to be able to collect all 21,000 cells simultaneously, the voltage, every 10 milliseconds. But also we can then actually change the mode of this battery and look at different aspects of it. For instance, looking at the inverters, looking at how the efficiency of the battery changes with the power it's delivering. But what we want to do in this project is take those algorithms we've been developing and know they work on a single battery, but how do they work across a range of different battery systems from different manufacturers, different integrators, different battery chemistries. And also with the data that Upside are currently collecting, which is generally quite top level, it's just kind of power and the state of charge of the system, what would the future requirements be to collect more data from that system to have a better understanding of how it's operating for enhanced diagnostics and prognostics? Next slide, please. Going back to the barriers of this data is, okay, so we now have a partner that has data, but they don't necessarily own that data. The Upside data sets are commercially sensitive. They've got people who actually are using their platform to control the assets, but they're controlling them under their own trading methodologies. So it is commercially sensitive. So what we tried with this project is something a bit different. We created the Python code and tested it on our own battery system. And then we packaged that code up to give to Upside to run on their own data sets using their own engineers. So they actually, in kind, provided that time to be able to do that. They then outputted the results and either give a kind of an overview of what the results look like or give some feedback to how it compares. So one metric would be they would know the capacity of one of the batteries it's been measured. Does our code produce the same capacity? And it would look at that over 2 or 3 years of data. We'd then go back to our code, iterate through, make some changes, and as it comes from, I'll talk about those in a moment. Then the process is repeated. So we're not actually taking those data sets, downloading them using ourselves. We're giving the code to Upside to run to get over this barrier of having access to much larger data sets. Next slide, please. So to the results, what I've shown here is some sort of simplified data. We actually worked with 8 large data sets, and the data streams we were using for this initial stage was power and state of charge. The algorithms that we were working with, we know they work very, very well, but we're used to working with DC linked voltage and current to take measurements of the batteries for advanced stellar charge, advanced stellar health, that sort of thing. So we're working with kind of the minimal viable data streams here. An example on this slide is the left-hand side is an output of a battery doing some cycling. This is a typical kind of battery cycling test you do, but with at 1.5 megawatt. And you can see the bottom chart is the state of charge. So taking these inputs, can we estimate the capacity? The right-hand side is showing that capacity. We know the capacity is about 970 kilowatt hours of this particular asset. So we're aiming between the 2 red lines, so 1% error. You can see it doesn't quite make it in there. Next slide. It's not bad though. This one shows another profile of a battery operating. This time it's not cycling. It's doing some different profiles. It's doing actually some efficiency tests and different power ratings here. So it looks a bit different. The point, you look at the state of charge graph, we have a period where the battery remains at a constant stellar charge pretty much, and then it drops down back up again. And we know that all the large systems out there being used have a very poor state of charge estimation. They don't use the kind of advanced algorithms that we are using in the labs and in research. So one of the problems with this kind of method is that you try and use power and try and use stellar charge. One of those data streams isn't actually very accurate. And also the power isn't necessarily accurate. It could come from the inverter, It could come from a power meter on the actual system itself. Next slide. So this where we end up in terms of that iteration of code actually is that we're not changing necessarily many of the parameters. We might be changing the window of the data sets we're choosing, but we're actually looking at more like a data selection. Can we choose particular parts of the data sets that we know give us a high confidence of a good result? This is what this example shows here. This is a battery providing dynamic frequency response service on the grid. And where I put the red circle, we've had a period of a stellar charge being quite settled, which with a traditional stellar charge mission BMS or big battery system will give us a reasonable result. And then we have a discharge. We've got a delta SOC, which means we can then measure that and measure the power. We can kind of work out the capacity, and that will give us a better result. For the capacity, we don't need to know the capacity as an updated value very often. It can be updated once a month, once every couple of weeks. Therefore, we do have opportunities to choose the data we're using to actually apply this algorithm to. And that's where we started to get some really interesting dialogue with Upside about how you could do this and when to do it. Next slide, please. So the results of this really were that we know with the current data sets, there's going to be a limit to how good it will work. It'll depend upon the types of operation the battery is under, to when you get high confidence data. But we know if we can get a few more data streams, such as the DC link voltage and current from the battery, we can get a better estimation of the state of charge using more advanced algorithms. We can also calculate the power from the battery, not the power going from the inverter, so we can avoid some unknown inefficiencies. In a lab situation, we can measure those. We can't when we've got a big grid battery. And then we can develop algorithms to selectively choose periods of good data. And that's where we kind of are now. And we're looking at all these different types of data we're using from Upside. There's a wide range of data update dates, samples. For example, the stellar charge wasn't taken at the same time as the power. It's not that important for this, but on the DC link, you want those two things to tie up. And we're also looking at, with the Upside platform, how you could take those then capacity measurements over time, link them to what the batteries are actually doing, then use that to look at predicting future degradation of those batteries, which is kind of the holy grail of then moving to the trading. Next slide, please. So next steps are to really identify some customers or asset owners that are willing to enter into a data sharing agreement. Although this methodology worked to get around this barrier of accessing that commercially sensitive data, it was slow. So depending upon the time that Upside could give to engineers to work with the code and do that work for us, whereas if we had the data, we'd done the next day. And then exploring additional data streams. So identifying some assets, some willing customers that are willing to send an extra few data streams, possibly us go and do some program on their systems to get those at the right kind of resolution and speed we need. We have a bit of follow-on funding to explore that data selection. We have just published a paper on the algorithms for capacity estimation on the DC link for large systems. And as part of that, it's been identified that we can probably come up with some machine-led methods for selecting that data, which could be interesting. And the diagrams at the bottom, left-hand side shows the three yellow points that we're measuring at the moment, which are the inverter power, reactive power, and stellar charge. And on the right shows what battery, if we have all those yellow measurements, that's when we do some really interesting stuff with some really accurate results. Next slide, please. So thank you for listening. I put some links on there to some data that we have uploaded for the Manifest project, which is data sets from the Willenhall battery, and we'll keep adding to that. Thank you.
Great, thanks a lot, Dan, for that. That's really great. There'll be no burning questions, and we are running a little late, so I'm just going to move straight on to Vijay, but that was great. Thank you. So Vijay, do you want to carry on?
Good afternoon, everyone. My name is Vijay, And I'm going to be talking about baselining for smart local energy systems. Andy Gilchrist for his support. Yes, next slide, please. So if you notice, I'm using the same icons that Malcolm used for his presentation. I think I can add a few more details to describe the problem. So in the past, like Malcolm said, you had power plants that were far, far away that pushed fuel into the furnace and then electricity into cables. But in the future, you probably are going to replace this with a much larger proportion of renewable energy sources. And the problem with these sources is that you can't decide when the sun will shine and when the wind will blow. So this means that you need new assets that will allow you to shift electricity in time in addition to shifting electricity in space. Why do we need to do this? This is because with renewable energy, you might have too little electricity or too much electricity. And this not only affects the way in which the grid functions, it also affects the stability and the reliability of the grid. So you need an asset that can absorb energy when there's too much and release it when there's too little. With these flexible assets, as you try to cluster smaller flexible assets, you're going to need a means to coordinate them. And our solution to this problem is a flexibility market. So a flexibility market allows us to match bids and offers between customers and suppliers of flexibility. What is flexibility? That in a sense is the ability to increase or decrease demand. So if you have a battery, when you're charging, you're increasing demand, and when you're discharging, you're decreasing demand. Thus, this flexibility market creates an incentive for previously passive players to participate in the market and help keep the grid stable. Next slide, please. So as with any market, there is a need to verify that the trades that were committed were actually executed. And by this, what we mean is that we need a way to gauge whether the battery which said it would deliver 50 kilowatts at 4 p.m. actually did it. Now, there's a simple fix to this, right? You can just hook up a meter to a battery, and that would be the end of the issue. Wrong. That's not the end of the issue, because the battery the owner of the asset may end up sucking the battery's electricity locally and making you pay for it anyway. So this is why we're hooking up the meter to the site instead of hooking it up to the battery. Now, if we know how much the site would have consumed if it did not provide flexibility, we can subtract that profile from what actually happened and figure out how much flexibility was provided by the battery. This is what is called baselining. So in a sense, we're creating a watchdog to verify the execution of trades in the flexible energy market. The main providers were DCC, who provided a secure communications line, and the University of Oxford. We developed the hardware and the algorithms that are related to this project. The main thing to look at is that there is an impact on the tools used and the communication link. Now, next slide, please. So this is something that hasn't been explored before. So baselining as a method has been discussed in other papers, but the relation between the secure communications link and the baselining tools and configurations of the architecture haven't been discussed before. So this is a barrier. Another barrier is that currently there is no incentive for stakeholders to collaborate in this system. And finally, there isn't a means to gauge the provision of flexibility using the existing infrastructure. Next slide, please. Next slide, please.
Sorry, one moment, it's just having a freeze. Stephen, would you mind taking over?
Yes. So there are three main components to this system. There is the measurement module, the secure comms link, and the command center. The The measurement module, in a sense, is a 3-phase power meter with a Raspberry Pi fitted on top. So the secure communications link was provided by DCC so as to not to compromise the safety and security of our asset owners. Finally, the command center processed the information received from the measurement module. Next slide, please. This slide presents a few results from the algorithms that were used for baselining. Essentially, when you're doing baselining, you're predicting what the demand would have been without flexibility, which means you have to compare the predicted value versus the actual value. This is what we're presenting in each one of the boxes here. The red line shows you an ideal case. So the closer the blue dots are to the red line, the better the algorithm. What that means is that if you were to look at the convolutional method, which is the second box in the second row, that did not do as well as the other methods, like, let's say, k-means or affinity propagation, when it was trying to predict the demand without flexibility. Next slide, please. There were two main lessons learned. The first one was related to edge analytics and data requirements. Mere measurement and communication of all of the data requires the transfer of a large amount of data through the secure channel provided by the DCC. And from our discussions with the DCC, if we were to use the existing communications backbone for the smart meter system, they would only give us 5 kilobytes for every half hour. So what we decided was that if you were to shift some of the computation to the Raspberry Pi, which is present within the meter itself, we can significantly decrease the amount of data that's required to be transferred. The second one was related to the measurement module. Now, commercial off-the-shelf technologies are better suited for large assets because trying to develop these modules on your own is more expensive than buying off-the-shelf units. As we move towards aggregation of a cluster of smaller assets, the development of in-house measurement modules are less expensive and allow for more customization. Next slide, please. Now for the next steps. So in terms of scope for improvement, we need to test the performance of individual models against more sophisticated ensemble models. In ensemble models, you use a group of algorithms and provide a prediction based on contributions from each one of those algorithms. Whereas in an individual model, you use only one algorithm and you rely on that to provide the prediction. We also need to extend the baselining algorithms to building assets where consumption depends on exogenous weather variables. In other words, we need to take into account changes in outside air temperature and solar irradiance when you're trying to account for the changes in the energy consumed by the HVAC system or the heating, ventilation, and air conditioning system. Finally, we would like to point out that there has to be a balance between local computation and data transfer to the command center. So this depends on how much value the data provides and how much you're willing to pay to send this across to the command center. Next slide, please. Yes, and that's the end of my presentation. Thank you for listening.
Thanks, Vijay. A quick question from Robin is, says, do politicians have an unrealistic expectation on the communication timescales, i.e. settlement time versus balancing act? DCC might be involved in delivering of flexibility services. So in other words, do the politicians realize how slow the data rates on DCC are?
I mean, I would say that things are picking up, especially because DCC has these GPS or GPS dongles, GSM dongles these days that can provide more data if you're willing to pay for it. So in that case, it's almost equivalent to an internet connection on your phone. So the rate at which the data is transferred is almost instantaneous. That should not be a problem. It's just that when you're trying to piggyback on existing systems which do not give you a lot of bandwidth, that you encounter problems. But I think that will go away in the near future.
Thanks very much, Vijay, and thank you for that one. Can we again just thank Vijay and in fact all the other speakers for their wonderful contribution, in the usual ways. Thank you.
Thank you.
Great. So we now move on to the next part of the program, and we're only 5 minutes late, which is not too bad, which is looking at the panel discussion. So the way we're going to arrange the panel is that each participant, which is Mel Bryce, Priya Bhagavati, and John Clark, each person is going to give about 2-3 minutes just to give some quick some thoughts on the role of data and IoT systems in the energy sector, and then we'll open it up to some discussions, which hopefully we'll get lots of questions through the audience. So Mel, over to you.
Yes, hello. Thank you, Malcolm, and thank you for inviting me to speak today and to be on the panel. I'm the Oxfordshire Programme Director at Scottish and Southern Electricity Networks, and we look very much after the wires and the cables, so from the cutout in your home right the way up to the grid supply point. So that's to sort of contextualise the organisation I work for and what it is that we're doing at the moment. So in Oxfordshire, we're looking at a project called LEO, which is Local Energy Oxfordshire, and very much looking at data and how we can use data to increase the levels of flexibility that there are with the assets in Oxfordshire, like Vijay was talking about. Now, this is very much pitched as the Internet of Things, and I have to admit to being someone who's not particularly technically literate when it comes to the Internet of Things. So I come from the pre-internet generation. If something starts with please download this app onto your phone, it used to send me into a spiral of despair. I've now got a teenage daughter, so she can help me, and my confidence levels are improving, and it's amazing how much can actually now be controlled by your mobile home in your actual own house. So there are sort of some issues around this. So for example, if your 5-year-old managed to get hold of your mobile phone, you might end up with a scene from the Sorcerer's Apprentice sort of springs to mind. So there's things that we have to be thinking about quite carefully in terms of behaviours and how we're going to actually manage this in the sort of day-to-day context. So, so for SSEN, we're predominantly looking at how we can help communities to thrive in this sort of environment for net zero. And traditionally, our load forecasts have been quite predictable. But now with the onset of electric vehicles and low carbon heating, for example, and people having more instantaneous control over their devices, those load forecasts are looking a little bit outdated. So part of the learning that we're getting from LEO is how these things are likely to change. So as we go forwards, we're looking very much at sort of smart technologies. So how can we monitor our network so that we can manage it better, so we can manage it in terms of time, as well as how much actual energy is flowing through, because at the moment it's quite a passive system and we want to make it a lot more sort of in tune to what is actually happening so that we can use the assets that are connected in a much smarter way. So one of the issues I think has been spoken about in one of the presentations is the complexity of the market structures that surround potential flexibility. So even just in the energy space, we've got someone who does the meters, we've got someone who does the supply, and we've got ourselves who do the distribution. And that's before you've even got to things like the apps that you've got to download in order to control your car, control your heating, you know, which may come from another organization. So there's a massive amount of complexity from, say, your internet-enabled kettle right the way through to your flexibility provision, say, at a primary substation. So that's one of the key issues that we want to be looking at. And the other thing we want to look at is trust with consumers. So ensuring that the value of the flexibility that is inherently going to be available through this IoT can be returned back to the people who are providing it. And for us, that would be a success.
Thanks, Mel. Priya, do you have any words, please?
Hi, thanks, Malcolm and the Pigeon team for inviting me to this panel session. I am Priya Bhagavati. I am a researcher in the Energy and Power Group at the University of Oxford. So my expertise is more on the energy system transition, looking at the whole system aspect, integrating technology, policy, and regulatory aspects. So what springs to my mind in this context are 3 projects that I've worked on called Desire, Park and Charge, and the Grid Edge. So our Desire project was also nicknamed as the Internet of Tanks, as in we use smart hot water tanks, which is asset, mostly available in UK. And in combination with batteries, how can we use this to provide demand-side response services? And one of the analysis that we did was just using these smart hot water tanks to absorb any excess electricity in the future. And we found that in future, when we have 100% renewables, kind of equipping 1 in 5 households in the UK with smart hot water tanks can absorb 80% of the excess renewables. So that's one of the analysis results that we had. And there are some assumptions that kind of constraints that go behind it, but that it was an amazing thing to discover that something which is as common as hot water tanks can be used to provide services, provided they are smart. And the other project is Park and Charge, which is an ongoing project which aims to provide charging infrastructure for people who will not be able to charge at home in UK. So approximately 30 to 40% of households, even if they buy EV, will not be able to charge at home because they do not have off-street parking. So in future, when we want everybody to be having electric vehicles or move to electric transport, where will these people charge? So that is one of the projects, again, that involves a lot of smart assets and a lot of smart communication, in that if we have, we are actually using car parks, where in a single car park, you have about 10 to 20 chargers, and each of them are fast chargers with 20 kilowatts. So that comes to about 200 kilowatt in a single location, which means that it is 1/5 of your transformer capacity. And if all the chargers are used at the same time without any smartness to it, then you will have an under voltage issue at the transformer. So this also will be integrated to the local energy project that Mel said in her introduction. The last piece of work which I would like to highlight is on the grid edge, where we looked at how do we say that a geographic region, especially as a country, is ready or in need for grid edge technologies. So by grid edge technologies, it means anything which is on the edge of the grid between the end of distribution to the customer. So it could be an electric vehicle, heat pump, solar panels, batteries, smart meters, to building control. So all these form a grid edge. And we used an extensive range of indicators to find out whether there is a need and readiness of these grid edge technologies. These help people to actually maximize the impact of the grid edge technologies. One of the things which I would also highlight based on this is the trust in technology among the people in UK is pretty low at this point. And even if we have these smart chargers or smart things installed, it is difficult to make user behavioral changes to convince them to actually use these smart assets. So I will leave that controversial statement.
Great, thanks for that, Priya. And then John Clark, any
Hi, can you hear me?
reflections? Yes, that's great.
Okay, can I just say thanks to, I'm John Clark, I'm the pitch-in PI for the consortium. So thanks to everybody there for really rather, actually more than 4 talk, rather good talks. I've really quite enjoyed them. Okay, so I thought to take a step back, I'd react a little bit to what I've actually seen today and just make some observations, but also actually throw into the mix some interesting issues which crop up in all modern systems, and that's security. And instead, that's also of interest to Oxford as much as it is to us, and some of the people from Newcastle are also on the call. So one of the things I would observe is that if you look at things like there are some architectural issues in security to be addressed, there's very little work around involving prosumers. Security work tends to be about people trying to steal electricity, not when you have additional capabilities of actually being able to supply as well as consume. We're going to face in security challenges all the stuff we know about, that's IoT and older ICS control system threats. But actually, there's an opportunity to take a step back and actually what is security in the context of these sort of systems? And I would suggest that security in these sort of systems that you envisage for distributed control, for example, and microgrids, is really anything that affects a business proposition that you choose to make. And that leads you to some very strange places which the security community habitually doesn't go down. Some observations which are fairly straightforward. We are going to face privacy and conflicts with optimality, and incidentally, one of the threats to these sorts of say microgrid system, anything which is to do with optimal or trying to achieve some non-functional goal of optimality, is a threat to optimality is a security threat. And I don't see that reflected anywhere in the security literature. There's some things which have sort of cropped up. People mentioned privacy. Yes, privacy is simply in conflict with optimality quite often, and you see these looking at in manufacturing and in other areas as well. Supply chains, for example, optimal supply chains actually depend on collaboration. And I think one of the interesting issues, which I think parts are actually beginning to deal with, is how you incentivize data sharing. The best way to get people to share data with you is to make it in their interest. So the question is, how do you actually incentivize data sharing in energy type systems? There's also issues with advanced persistent threats. One of the things you will face with these systems is that when people are part of the system, and you're talking about entire populations, largely if you have a national rollout, you have a lot of potential insiders. And so the insider problem in security manifests itself greatly. I enjoyed the bit about essentially standardization and how do you actually curate data for more general use and general particular research use. So I started thinking about standards and their role in security. Well, standards, there are people who wander around the country talking about standards as if they were a good thing, right? Okay, what do I mean by that? Well, of course, the idea of standards is you write once and you use everywhere. That's the operational efficiency you actually get from having standards. From a security point of view, it's break once, break everywhere. And this, if there are energy systems which are going to be rolled out, if you have microgrids across the country, linked into the national grid, etc., in a whole national system, then you have to consider the consequences of standardization, which is if something is wrong, you can blow the network apart nationwide, essentially, is what it was. So break once, break everywhere is a security, a rather sarcastic one, but it's a security view on standardization. So consider things like national rollout, and when you actually scale, what are the security threats which actually arise from scaling? There are issues clearly with legacy and security, and interesting, some of the things which I have a big interest in, hard real time poses real security issues. When you have very, very tight deadlines, what are the consequences for the security that you can actually provide, which is consistent with those messages getting through, so you actually have a limit latency within the deadlines which are actually there. So that I think there are real, more generally with computer science type issues, hard real-time security issues, hard real-time issues, and security issues as well. There's also the big issue which we're going to face, which is, people mentioned legacy. There's also what you're doing at the moment, because what you're doing at the moment will be legacy in 10 years' time, how you actually evolve. And in the traditional problems with IoT, you're going to face all of those, and that's how do you actually do secure updates, because you always want to upgrade. How do you do upgrade securely? One of the things I thought was really important, which came out, which I think it was Dan who emphasized, is essentially the importance of quality software engineering and systems engineering, both for research integrity, but actually from a pitch-in perspective, the role quality demonstrations and quality software has in actually facilitating innovation and transition. And so it has that downstream effect, as if the software is good, it's much easier to demonstrate, people have much more confidence in, and Taker will be much better later. So you invest now in quality software engineering in order to get many of the benefits downstream. And just actually looking, my final comment would be, my immediate reaction to an awful lot of what's in is very much the zeitgeist. Ask not what you can do for operations research and ML, but what operations research and ML can do for you, and be eclectic about that, as well as doing the optimizing and optimizing classifications, for example. There's opportunity to get real insight, and the question is how you systematize that into a research program, looking for insight into sorts of systems in very different types, whether it's batteries or whether it's microgrids or whatever, how you get insight into those, because that insight can be very valuable. And I'll leave it there. I've really enjoyed listening to the talks today. Thank you. Great.
Okay, so some of those of you who are actually watching the clock, we realize that we are at 3:30, which is the end of the time. However, what I'm going to suggest is, because we've got some really interesting people on the panel, is that if you need to leave, then that's fine. Otherwise, we're prepared to stay on for another 5 or 6 minutes, if that's okay, and we can actually answer some questions. And then that would be really good. So, so one of the questions I'm going to start off with, and if you have any questions please put some in the chat function. I'm going to pick up on something that John said. So John, you don't need to answer this. I'm going to aim it mainly at Mel and Priya to start off with. Is the role of privacy and privacy enabling algorithms, and how important do you think that's going to be in the energy system as we go forward? And Mel, I'm going to ask you to start with that, please.
Yeah, I think it is going to be incredibly important. How do we do this? You know, how do we make sure that people can benefit from the technology that's available and the market structures that we're going to be putting in place so that we can get to net zero without infringing on people's privacy? I think it's something that we're really going to have to grapple with as we go forwards. You know, there's a lot of people put a lot of information on their social media feeds and don't really think that much about it, but as soon as someone wants to access, you know, the data as to when you're using your kettle, for example, there's a whole different attitude in play there. So I think there's a sort of an education piece that has to be done in order to see that, you know, where we need to get to, and sort of baselining it against what other people, what you have across other sort of parts of your life, as it were. So I think it's definitely an area that we need to work on, but not just from the kind of legislative angle, but also from the educational angle as well.
Yeah, I think that's great. Priya, any thoughts on your side?
Yeah, I agree that role of privacy is really significant, and especially once it comes to the energy use in your own homes, there is issues related to both safety of the person inside the house, as well as in terms of within the household, how many of the other people would want to know about the usage, as in it could even trigger a domestic abuse if not handled properly, as in if there are two people in the house and one of them doesn't know what time speed the other one is coming, and if there is a close monitoring, then that would trigger an issue. So this is really controversial to also determine like how much of this data should be shared. It might be that it has to be shared with the utility company or the balancing market mechanism. That is fine, but how much of this would be available to other people to view? So it also is a bit about how much. So maybe we can also look at that the data is shared, but not at that granular level, both on time and space with every other person. So there are privacy concerns on both the safety as well as what level it is.
So John, the slight variation I'm going to ask with you is to say, if you layer on top of privacy, there's also got to be some layer of monetization to be able to pay for the IoT network in the first point. Do you see a conflict between those two, or how do you see those two working together or against each other, both privacy and monetization?
Okay, so I think for me, there are a number of issues that actually came up with that. And so just to respond to what I've heard.
Yeah, go for it.
Yeah, okay. Issues of incentivization are important. I think we can have to sit down and work out what incentivizes data to share. There are also ethics considerations, because the common or garden user really doesn't understand essentially, please sign here, otherwise your app doesn't work. Click. And when we're in a situation when it's not clear what the consequences of agreeing to processing by we don't actually fully understand the power of AI or machine learning. So when you say, yeah, I agree to that, you agree to that as in to do it, but you don't actually agree to what the consequences are, because people don't actually fully understand the consequences. So I think there are real issues of ethics and consent, and it's not just consent, I tick the box, it's informed consent, and how you actually get informed consent from the population in the light of what are essentially complex systems is a really tricky issue. I think there are all sorts of conflicts which will arise, and that's why this notion of shared investment and shared, I give away this and I also get this back in return. And the question is how, just following up on one of the comments made, is how you agree that shared framework and how you detect abuses of it, and that's going to be really tricky. I give personal data away all the time. Absolutely all, and we all do. It's called credit card information. You give your credit card information away, or you used to, or whatever. The implicit thing is you give it away for a particular purpose. It is for that transaction and that transaction only. It's how you actually, can you actually detect, and I think it's a big research issue, how you can detect deviations from contract, what you agreed to give your data for. If I say you can use it for X, you use it for X, that's fine. If you use it for X plus a little bit of Y, that's a breach of privacy, because privacy is largely about not just confidentiality, it's about control over its use. There are big issues, but I think the incentivization part and trust and how you actually encourage people to do it, and the big difficulty for me, and I just don't know how to do this, is to do it in an informed way without being literally very patronizing. Yeah, I'll make decisions for you, but there are some big issues in that area.
Yeah,
there are some technical solutions. Fully homomorphic encryption may help. There are some AI people out there working on split learning and federated learning, ways of actually noising what goes on at each of the possible inputs to the system in order to enable a global view of the system. There are some technical fixes coming downstream. Fully homomorphic encryption, in other words, you can supply data, but no one sees the data, but it's done unencrypted. You then get the answers back encrypted, so you can do the computation anywhere. That's a really important technology. Unfortunately, as I understand it, it runs like a drain at the moment. so I wouldn't hold. The cryptographers might disagree.
Mel.
Yeah, I was going to say there's also a big issue over who owns the data. You know, who owns your own data? Can you get your data? Who do you have to go to get your data? These things are at the moment unclear, and if you can't be in control of your own data, then it's hard to know, you know, what it is that you are and are not supplying. So it goes back to the consent and the informed consent part again, and that's something that we are looking at as part of the LEO project, is how to get hold of some of the data that we need.
Yeah, to add on to that, like not just who owns the data, as in like at what granularity you can view your own energy usage data for the entire household. So the smart meter for a house is only one. So it gives, if you are really looking at very granular data, it gives away much of the occupancy information. So if it is a household, to what level can the householder view the data? So that is one aspect which I wanted to highlight. On the other is like the major players like Amazon and Google coming into the energy market. They already have sufficient information about our practices, our website searches. So they already own a lot of our data. So with the ability for them to monitor our energy usage as well. So you're mixing those two together. It's a very dangerous mix, as in like it feels a very bit scary to me personally to say that they already have dropped me cookies without even letting me know what the cookie meant. And I recently discovered that when they drop in a cookie, it also means that I am giving them permission to pass on my information to 100 other sites. So it's like they already have this big set of data and information about me. And now my energy supplier has the data with them. So it is, if we do not have the ethics properly done in place and the confidentiality in place with the informed consent, then it is going to be a hell lot difficult to convince those who do not test technology in the current phase to then move into a smart phase.
That's great. Okay, we've had our 10 minutes, so can I just say thank you very much to the panelists. I think that was a really interesting thing to close off the panel with. So, you know, just to quickly recap, is we realize that IoT is going to be critical in the part of the future energy systems, you know, right down from monitoring individual batteries all the way through to, you know, potentially being the backbone of future markets. We saw in the 4 presentations of the projects is that, you know, we're looking, IoT plays a role, everything from, you know, homogenizing data from disparate sources with different regimes and putting it all into one consistent format that we can then access, through to looking at how do you then look at, you know, large, you know, tens of thousands, hundreds of thousands of devices, and how do you collect that information, and how do you do that in a privacy way where you might not just be sharing data, but you might be sharing code, which is quite an interesting way of going around it. And then also looking at the second and the last one also picked up around the speed of the internet and how, and the speed of comms and how that might be limiting, even in very different contexts. You know, one was looking at the millisecond context and the other one was looking at the kind of, you know, 10 minutes context, but both of them had data constraints in terms of the capacity that needed to come through and how does it work through that. And then there's fantastic panelists to really explore some of the challenges around the privacy, and this is going to be a real big issue that I think is coming through. And I know there's some of the, you know, homomorphic encoding protocols are coming through, which is going to help with that, but I still think this is going to be something that's going to be really interesting and challenging. And then lastly, I'd just like to thank Research England for being able to underpin everything. We have some more events coming through. Please have a look at those. And very lastly, I'd just like to thank Elizabeth and Stephen for running this for us and to being so deft in managing the challenges of the technology. And as a last thing, can we just give a clap to all the participants, and we say really thank you to everybody. And I wish you a fantastic rest of the afternoon. And if you're like us, maybe the sun's shining where you are. And so congratulations and have a fantastic day. Thank you very much.